Hi, this is John Isles and welcome to Geometer's Paradise. Today we're going to talk about Unit 7, Lesson 1, the Perpendicular Bisector Theorem and the Circumcenter Theorem. We have four goals, basically: to use the Perpendicular Bisector Theorem to solve problems, to use the converse of the Perpendicular Bisector Theorem to identify a perpendicular bisector, to prove the Perpendicular Bisector Theorem and its converse, and to prove the Circumcenter Theorem. Okay, the first thing we need to talk about is a definition here for perpendicular bisector. A perpendicular bisector is a line, or part of a line, that intersects a line segment such that, number one, it intersects the segment at its midpoint. You see here the yellow line is intersecting at the midpoint. The segment here from A to the yellow line and from B to the yellow line are marked congruent with this hash mark. And the line is perpendicular to the segment, and we see that here. So we're perpendicular. So we are a perpendicular bisector. Now, the perpendicular bisector theorem says this: if I were to pick any point on the perpendicular bisector, any point on the perpendicular bisector, like maybe I choose this point right here, okay? If I were then to measure the distance from A to that point or from B to that point, then I would find out that these two line segments are congruent. So let's suppose this point is called D. Then AD is congruent to DB by the perpendicular bisector theorem. Okay? So AD, nope. AD is congruent to DB by the perpendicular bisector theorem. Sorry, my pen is giving me a little grief. All right. So how is this used? Anytime we have a perpendicular bisector, we can choose a point on the bisector and the segments are the same length. So this problem shows up with algebra like this. Here we have two line segments. Let's call this AD and DB again, with the points 5x plus 18 and 7x minus 10. Our goal is to set these equal, but we can't without the perpendicular bisector theorem. Since the yellow line is a perpendicular bisector, we can say AD is congruent to DB, perpendicular bisector theorem. So 5x plus 18 is equal to 7x minus 10 by substitution. Then 2x is equal to 28 and x is equal to 14. Sometimes a problem will ask you to plug this number back in, so you just put it back in. This would be 14 times 5, which is 70, plus 18. So this is 88 units. And we see over here, if we do the same thing, 14 times 7 is 98, minus 10 is 88 units. Okay? So there you go. So this is using the perpendicular bisector theorem. This is the kind of algebra you could expect. But of course, using it is not what we're here for. We're here to prove it. So what we want to do is place a point D, place a point D somewhere on the yellow line, like so. So here's point D. And then place M at the intersection of the yellow line and AB. So DM is perpendicular to AB, and DM bisects AB. We want to show then that the segments that connect AD and DB are congruent. So I want to show that this segment is congruent to this segment. Right? You should see here we're looking at a side angle side proof. We have the two sides created by the bisector. We've got the right angles created by the perpendicular part, and of course we have the reflexive side. So AM is congruent to MB because of the bisector. We have MD congruent to MD by the reflexive property. And we have angle AMD congruent to angle BMD by the whole perpendicular line thing. So remember, perpendicular lines create congruent adjacent angles. So the triangles are congruent. I'm going to select triangle MAD, and it's going to be congruent to triangle. Now I went middle, outside, top, so I'm going to go middle, outside, top. MBD, this is by side angle side. Now, CPCTC is an interesting result. See, the whole point of doing triangle congruence is to know that all of the parts of the triangle are congruent. So I use the first three pieces of the triangles to show the congruence. And that means I have three more pieces congruent now. So there are three more potential congruences based on this. We show triangle congruence, we unlock them. One of them is that I can show that angle A and angle B are congruent. I can show that angle ADM and angle BDM are congruent, or I can show that AD is congruent to DB. So which one do I want? I want AD and DB. So we say AD is congruent to DB. Corresponding parts of congruent triangles are congruent. Whoops. That's right, I can't do that. Okay. There we go. So that's your proof for the perpendicular bisector theorem. The converse of the perpendicular bisector theorem says that if I have a point, E, that is equally distant from either side of a line segment, then it's going to be on the perpendicular bisector. So the idea here is that if I draw this line segment, E, okay, this point, and it goes through perpendicular to the center, then it's going to be on the perpendicular bisector. So we draw E in one of two ways. We draw it so that it goes through the middle, and this is congruent to this, or we draw E as an altitude of this triangle so that we have the right angles. It works both ways, except we actually haven't learned about medians yet. So what we're going to do is draw this as an altitude, and then we can write the proof. Notice that we have the hypotenuse of right triangles on both sides, okay, the legs, and of course the right angles. So this is a hypotenuse leg proof. Okay, our first step is to connect E perpendicular to M. So we draw an altitude for the triangle, and that gives us right angles on either side, and we name this point M. So we say then that angle AME and angle BME are both right angles. The reason for this is because of the altitude. An altitude is perpendicular, and perpendicular produces right angles. The hypotenuse is given. AE is congruent to EB, given. And the leg EM is congruent to EM, reflexive. So we say triangle AME is congruent to triangle BME by hypotenuse leg. And again, CPCTC. Now, our goal is to show perpendicular bisector. We have actually already achieved perpendicular from this line right here. Okay, we drew an altitude, and that gives us perpendicular. So what we need down here is some kind of statement to suggest that we're bisecting this side. Okay, that means I need to know something about AM and MB. So we say AM is congruent to MB by CPCTC. So EM is a perpendicular bisector of AB. Okay, explanation of the results here real quick. We can produce the perpendicular bisector because of two reasons. Remember, as we said in the last slide, the altitude is what suggests perpendicularity, and we get that by choosing to draw EM as an altitude. We got to choose that. We could have also picked EM to be a median and still achieved our result by proving perpendicularity. But this just happens to be the approach we took this time around. So we drew an altitude, which is perpendicular. And then we show by CP/CTC that the two segments are congruent. And this is what produces our bisector. Okay, this is the very first time that a proof required two results in order to finish it off. All right, now it turns out that if I draw the perpendicular bisectors of a triangle, okay, that they will, of the sides of a triangle, that they will meet at one point. So what we have here to start is we have the midpoints of each of these sides. So knowing the midpoints of each side, I draw a line segment that's perpendicular to that side, and I've got some guidelines here to help me out. So I draw a segment from the midpoint, all right, perpendicular to the side. So this first one looks like this, and it's perpendicular. Okay? And if I do this from each side, drawing these perpendicular segments, okay, then what we notice is that all three of the perpendicular bisectors of the sides of the triangles will meet at a single point. And this point is called a point of concurrency. All right, so the perpendicular bisectors of a triangle are concurrent. Now, in order to be concurrent, you have to be three or more. Two lines are never concurrent, and they meet at a single point. So the perpendicular bisectors are concurrent. From here, we can write a simple proof. Knowing that the perpendicular bisectors are concurrent, and that we have the perpendicular bisector theorem, which says that if I have the perpendicular bisector, then any point on it, like D, is equally distant from the sides of the triangle. So let's draw for a moment the sides AD and DC. AD and DC lie on D lies on ED, which means AD is congruent to DC. So let's write that down over here. I know that AD is congruent to DC by the perpendicular bisector theorem for perpendicular bisector ED. Now, if I go over to perpendicular bisector DF, I have another line segment. Because D is on F, that means that DB and DC are the same length. So I can say that DC is congruent to DB by the perpendicular bisector theorem for line segment or bisector DF. And by the transitive property then, AD is congruent to DB. This is actually interesting because while I can do transitive to connect the two, I also have the choice to do another perpendicular bisector theorem for DG. And that would tell me that AD is congruent to DB. So now all three of these segments are congruent to one another, which is kind of cool, right? Because anytime you have a situation like this, one point with three congruent segments, that indicates that we could draw a circle because the radii are line segments that all come from the same point. And so what we see next is that I can do something called circumscribe. Circum means around, scribe means to draw or to write. So circumscribe means to draw around. And a polygon is circumscribed when the circle is drawn so that it touches all three of the vertices of the polygon. Notice here I drew a circle with center at D, and it touches A, C, and B. So this yellow circle circumscribes the triangle ACB. Because point D is at the center of that circle, we call it the circumcenter. It's the center of a circle that goes around the triangle. All right? So it's the center of the around circle. All right, so we call it the circumcenter. The circumcenter can be used to perform calculations. So suppose I have a problem that says that D is the circumcenter of triangle ABC. Then what that means is that DC is equal to DB. So I can go 4x plus 12 equals 9x minus 13, which gets me 25 on the left and 5x on the right, so x is 5. That in turn means that the length of DC is 32 units, and likewise the length of DB is 32 units, which means the length of AD is 32 units. So AD is equal to 32, and we also know that AD is equal to 4y, which means y has a value of 8. So you can use the circumcenter to perform calculations that way. All right, now we're done with that. Let's take just a second here. Fire up GeoGebra for a second. What I want to do here is show you how the circumcenter works. Here's a polygon, and I'm going to draw the perpendicular bisectors to each side. Notice that they meet clear down here. This point, point D, is the circumcenter for the polygon. I can use it to draw a circle that goes around the polygon. All right? So this is the center of the circle. Watch what happens as I drag the points of the triangle. Notice that the circumcenter changes. It even goes outside the triangle. It's still outside the triangle. That's pretty cool. And so we can move it around, and it exists on these bisectors, these perpendicular bisectors. Okay? So what we learn here is that the circumcenter can be both inside or outside the polygon. All right, there you go. We'll see you tomorrow in class.